change in concentration of the reactants or products per unit time is called the rate of reaction. In the organic reactions or molecular reactions, what will happen? Bond breaking first, then bond making. For both the things, it needs time and energy. The concentration of reactant side is going to increase. Automatically, the rate of reaction will increase. After attaining equilibrium, what will happen? From the backward direction or from the forward direction, same state of condition, that is either in temperature or pressure, reactant side and the product side will be the same. Hello everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today I am going to start session 2 from the chapter Chemical Equilibrium. In the last session, we have discussed the introductory points of chemical equilibrium and its physical equilibrium, chemical equilibrium. These are the two types of chemical equilibrium. This we have discussed in the previous session. In today's session, we will discuss about rate or velocity of a reaction, law of mass action and law of chemical equilibrium and equilibrium constant. These are also important concepts to understand overall equilibrium or overall how the reaction will proceed, how the reactant and product will work upon the reaction. So, before to understand, you have to know these concepts. First, we will see rate or velocity of a reaction. The change in concentration of the reactants or products per unit time is called the rate of reaction. If any change is going to happen in reactant or a product per unit time will be considered as rate of a reaction. As I told earlier, rate means nothing but time in the chemistry terms. Example, consider a reaction A is going to happen a product. Okay, let the initial concentration of the reactant be C mole dm per cube. Okay, let dC be the small change in the concentration of the reactant or product in a small interval of time. See here we have we know that let the initial concentration be the C. Okay, that we are going to convert into dC. What is the dC? D is nothing but delta. It is a small change either in reactant, concentration of reactant side or concentration of product side at a small interval time of dt, changes in time. What our definition is, change in concentration of reactants or products per unit time. This concentration is going to have a small change with respect to this time. Then the rate of reaction will be R decreases in the concentration of the reactant or increase in the concentration of the product. This is rate of reaction. Small r will be rate of reaction. From reactant to product is going to happen. Then what will happen? Decrease in concentration of reactant side and increase in concentration of product side. Okay, one or the other step will happen. That is R equal to minus dC by dt with respect to the reactant. Because concentration of reactant will be decrease. So, minus dC by dt, that is with respect to time, to the reactant. The negative sign indicates decrease in the concentration of reactant with time. Why this negative sign? Because this concentration is showing to the reactant side. So, concentration of reactant is going to decrease. So, negative sign. If it is going to increase in product side, that will changes to positive sign. See here, the positive sign indicates an increase in the concentration of the product with time. As I told, either in reactant side the concentration will decrease, either in product side the concentration will increase. If it is decreasing in reactant side, the sign will be negative, the rate of reaction will be negative. If the concentration of product side is going to increase, the rate of reaction will be positive sign. Okay, the rate of reaction is expressed as mole per dm cube per time. This is the expression which we'll use for a rate of reaction. Next, factors influencing the rate of a reaction. What are the factors influence the rate of reaction? Usually what are nature of reactant, concentration of reactant, catalyst and temperature. These are the 4 factors which will affect the rate of a reaction. nature of reactant, concentration of reactant, temperature and catalyst. These are the 4 factors and we'll see now how it will affect. First, nature of the reactant. In general, ionic, that is inorganic reactions are fast and molecular, that is organic reactions are slow. This thing we know, inorganic reactions are little bit fast comparative to organic reactions. Okay, in the reaction between ionic substances, the reacting substance exists in the form of free ions in solution and readily interact to give the products. Hence, such reactions are instantaneous. Usually, ionic will be free ions and whenever the reaction is going to happen, it will fastly give the formation of product. So, it will be instantaneously happen. In the reaction between the molecular substances, bond breaking is essential and it needs considerable time and energy. Hence, such reactions are slow. In the organic reactions or molecular reactions, what will happen? Bond breaking first, then bond making. For both the things, it needs time and energy. So, what will happen? For molecular reactions or organic reactions, it takes time and energy and the time will lag for some time. In fact, ionic reactions are so fast that their rates cannot be measured. Hence, the idea of reaction rate is applicable only to molecular reactions. In so many reactions with respect to inorganic reactions, they are so fast, so we cannot judge or we cannot measure the rate of reaction. So, what we have to understand, rate of reaction will be considered in terms of only organic reactions. Next, concentration of reactant. The rate of a reaction increases with increase in concentration of the reactants. Okay, rate of reaction when will increase? When the concentration of reactant will increase, both will increase. So, what we have to understand, the rate of a reaction is directly proportional to the concentration of the reactant. This is explained using collision theory. According to this theory, reacting molecules must collide with each other to give the products. With the increase in concentration of the reactants, the number of collision increases and thereby the rate of the reaction will increases. Here, concentration of reactant, how it is affecting? Once again I am telling, when the concentration of reactant side is going to increase, automatically the rate of reaction will increase. How means? It is depending on collision theory. Collision theory means nothing but when molecules are getting to collide, it will form product. Whenever the collision will going to increase, their product formation is also going to increase. Before that, concentration of reactant will also be increased. Therefore, rate of reaction is directly proportional to the concentration of reactant. Okay. Next, temperature. The rate of reaction increases with increase in temperature. This may be also explained using collision theory. According to this theory, reactant molecules must possess a certain minimum amount of energy to undergo a fruitful collision. This energy is called threshold energy. With increase in temperature, more number of molecules attain threshold energy and thereby undergo fruitful collisions, increasing the rate of reactions. Here also the collision theory will apply. Okay, whenever the rate of reaction is increased, it will be done by the increase in temperature. Okay, the minimum amount of energy will be needed. That energy will be called as threshold energy. Okay, by this threshold energy, collision will happen. Okay, by that collision theory or colliding of molecules, obviously the rate of reaction will increase. Next, catalyst. A catalyst is a substance which alters the rate of reaction without undergoing a permanent chemical change. What is catalyst? It is also a substance which will alter the rate of reaction without undergoing its physical property or chemical property. A positive catalyst increases the rate of reaction and the negative catalyst decreases the rate of reaction. There is also two types of catalyst. Positive catalyst increases the rate of reaction. Negative catalyst decreases the rate of reaction. This is how the 4 factors also affect the rate of reaction. Next, law of mass action. Okay, this was proposed by Goldberg and Wage. The rate of reaction is directly proportional to the product of active masses of the reactants, each raised to the power equal to their stoichiometric coefficients as indicated in the balanced chemical equation at constant temperature. What they are telling, law of mass action means, this is the statement, the rate of reaction is directly proportional to the product of the active masses of reactant. How much mass you have used actively in the reaction, that much will be directly proportional to the rate of reaction. If you increase the active mass of reactant side, obviously the rate of reaction will also change in the stoichiometrically and also in a rate of reaction wise. We'll see one example. Consider a reaction A is going to give product. See, a rate of reaction is directly proportional to the concentration of reactant, where this concentration of A will be equal to active mass of A. Active mass is the molar concentration expressed in mole per dm cube. Okay, this is the expression, and this active mass will be the molar concentration of the reactant. And this proportionality should be identified with some constant. That's why here K will be introduced. Now, rate of reaction will be equal into rate constant into molar concentration of A. See here, K is nothing but rate constant. If concentration of A will be equal to 1 mole dm cube, then R will be equal to K. That is, the rate constant is equal to the rate of the reaction when the molar concentration of reactants is unity. This is called specific reaction rate. What they are telling, if reactant is at unity, obviously R will be equal to K. Okay, this is called specific reaction rate. Next, consider a reaction. This is stoichiometric. Okay, XA plus YB giving to product. We know that R is directly proportional to the active masses of reactant. This is the stoichiometric numbers. So, they have coefficients, they have written in the above. R will be equal to K into A into B, concentration of A into B, where X and Y are respectively the number of molecules of A and B participating in the reactions. How many number of molecules? Particularly, they are involving in reaction. Law of chemical equilibrium and equilibrium constant. Okay. According to the law of mass action, the driving force of a chemical reaction is proportional to the active masses of the reacting substances. It is assumed that the active mass is equivalent to the molar concentration. See, you have to understand how much reactant is there, that much driving force will be applied. If the reactant is only less, if you are applying more driving force, means it is useless. So, the driving force will be directly proportional to the active masses of the reactant. By that, it is assumed that active mass is nothing but equivalent to the molar concentration. Okay. Law of mass action states that the rate of a reaction is proportional to the product of active masses of the reactants, each raised to the power equal to its stoichiometric coefficient as represented by the balanced chemical equation. At the power, what we have written? Number of molecules. If the number of molecules is going to increase in the stoichiometric equation, obviously we have to increase in the product side also, because we will get the extra more product. In simple terms, it means that the rate of chemical reaction is proportional to the molar concentration of reacting substances. By the above point, what we will understand? The chemical reaction is directly proportional to the molar concentration of the reacting substances. If the molar concentration of reacting substances is more, obviously chemical reaction will also get more. Next, law of chemical equilibrium and equilibrium constant. This law is applicable in most cases, though it is not universal. So, though it is not universal, the equilibrium law, but many of the reactions will be applying by this law. Applying the law of mass action to an equilibrium reaction, see here, A plus B giving to C plus D. We have RF, which is rate of forward reaction, is directly proportional to the A molar concentration of reactants A plus B. This is rate of backward reaction directly proportional to the molar concentration of product, that is C into D. Let Kf be the rate constant for the forward reaction and Kb be the rate of backward reaction. Then what will happen after summarizing all the things? Rate of forward reaction will be equal to rate constant of forward reaction. This is molar concentration of reactant. Same here, backward reaction into equilibrium constant for backward reaction into products, molar concentration of products. At equilibrium, Rf equal to Rb. So, K equal to Kf by Kb equal to product, molar concentration of product by molar concentration of reactants. This expression is the law of chemical equilibrium. K equal to Kf by Kb. This is the equilibrium constant. Usually, where you are relating with equilibrium constant or rate constant, usually molar concentration of the product will be in the nominator side and the molar concentration of the reactant will be in the denominator side. How it will be represented? By using this formula. Okay. Next, equilibrium law or law of chemical equilibrium. What is that statement? By analyzing those so many points. At a given temperature, the product of concentrations of the reaction products raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the product of concentrations of the reactants raised to their individual stoichiometric coefficients has a constant value. Okay. What we have explained by before showing so many points or examples, after analyzing those points, this is a statement. When the active masses of reactants and products are expressed in molar concentration, the equilibrium constant is represented as Kc. When the reactants and products are expressed in molar concentration, the equilibrium constant will be represented by Kc. On the other hand, when the active masses are expressed as partial pressures, it is represented by Kp. If it is in reactants or products in molar pressure, that time Kp will be indicated. Active masses of solid as well as excess of pure liquid are taken to be as unity. Okay. If it is expressed in molar concentration, by Kc you have to identify. If it is in partial pressure, then you have to express by Kp. If little bit more solid or liquid, then should be identified as unity. See here, expressions of equilibrium constant for some reactions. This is nitrogen and hydrogen giving ammonia. This is product, right? Molar concentration we are analyzing. So, forward reaction by backward reaction. Here also by partial pressure, forward reaction by backward, and product concentration of product by concentration of reactant. Here partial pressure of product by partial pressure of reactant. Here also hydrogen and iodine giving hydrogen iodide by molar concentration by partial pressure. Here also sulfur dioxide plus oxygen giving sulfur trioxide. Here also molar concentration. Here also partial pressure. Everywhere you have to first write the forward reaction, that is product, concentration of product by concentration of reactant. This is with respect to molar concentration. This is with respect to partial pressures. All the 5 examples showing molar concentration, partial pressure, and how you have to write the overall equation by seeing the balanced chemical equation. Next, characteristics of chemical equilibrium. Equilibrium state can be attained only if the reaction is carried out in a closed vessel. Equilibrium reaction will be happen only if the reaction is going to happen in a closed vessel. Equilibrium can be attained from either side of the reaction, that is, the same state of equilibrium will be reached under the same conditions of temperature and pressure, whether the reaction is carried out from the forward side or backward side. What they are telling? Equilibrium can be attained from either side of the reaction. If from forward direction also, it is from backward direction also. That is, the same state of equilibrium will be reached under the same conditions of temperature and pressure. After attaining equilibrium, what will happen? From the backward direction or from the forward direction, same state of condition, that is either in temperature or pressure, reactant side and the product side will be the same. Equilibrium is dynamic in nature. That is, the reaction does not stop at equilibrium, but both the forward and backward reactions takes place at equal rates. It will not stop after attaining equilibrium, but both the reaction and reactant and product will run in the equal rate. The rate of forward reaction is equal to the rate of backward reaction. After attaining the equilibrium, the rate of forward reaction and the rate of backward reaction will be the same or equal. Next, all measurable properties of the system remain constant. That is, after the attainment of equilibrium, there won't be any further change in the concentration of either reactants or products with time. After reaching equilibrium, either in the reactant side or in the product side with respect to time, any measurable quantity like temperature, pressure, volume, anything, it won't change. It will be constant. A positive catalyst can only help in quick attainment of equilibrium but does not alter the value of equilibrium constant. After attaining equilibrium, if you add positive catalyst, what will happen? A quick attainment means quickly it can complete the reaction, but it will not alter the value of the equilibrium constant. Positive catalyst will alter only the time, not with the value of equilibrium constant. Change in temperature increases or decreases the equilibrium constant. Change in temperature will increase or decreases the equilibrium constant. Okay, why we are analyzing these things means, before we have discussed that factors affecting the equilibrium or equilibrium constant, that is nature of reactant, concentration of reactant, temperature and catalyst. So, by that factors we are correlating with points what will happen after the attainment of equilibrium, the how will reaction will change, either will change or not. Next, some facts about equilibrium constant. After knowing all the characteristics of equilibrium constant, there are so many few points about equilibrium constant. The equilibrium constant of a forward reaction and that of its backward reaction are the reciprocal of each other. See here, this is the equilibrium arrow mark and this is in the reciprocal, means after the attainment this much concentration will be equal to this much. Okay. If the stoichiometric coefficients in a balanced chemical equilibrium are multiplied by a common factor, the new equilibrium constant must be raised to the corresponding factor or power. If it is multiplied by some common factor, then power will be changed. See here, 2NO, the power will be changed or raised. Okay. Next, if the stoichiometric coefficient in the balanced chemical equations for the equilibrium reaction are divided by common factor, then the new equilibrium constant will be corresponding or cube root of the old one. See here, if for N2 plus O2 will be 2NO, the equilibrium constant is K. Then half N2 half O2, NO will be the root of K. Here, multiplied by the number of power how much you have used in the coefficient, here root K or cube root will be used. When a reaction takes place is in more than one step, the equilibrium constant of the overall net reaction is equal to the product of the equilibrium constant of each step. If any reaction is not completed with one step, it may take 2 or 3 steps. In all the step products will be attaining, the overall number of products will be given, the last overall net product. See here, this is around 3-step reaction, means A is going to give B, B is going to give C, C is going to give D. At the end, A will give D, right? So, this K1, K2, K3, overall K will be K1, K2 and K3, that is the net reaction and net equilibrium constant. A large value of Kc or Kp signifies that the forward reaction as written goes to very nearly completion. On the other hand, a very small value of Kc or Kp signifies that the forward reaction as written does not proceed to any significant extent. Kc means you know, equilibrium constant at molar concentration. This is rate constant at partial pressure. If it is changes with large value, then forward reaction will also changes in more value. Okay, at least it will reach near completion. If it is in the small value, it will not change to the significant value. For a given reversible reaction at a fixed temperature, the equilibrium constant at Kc and Kp are related by Kp equal to Kc into RT to the power delta N, where delta N will be equal to number of moles of gaseous products minus number of moles of gaseous reactants. This formula is very much important. Kp equal to Kc into RT to the power delta N. That delta N is nothing but number of moles of gaseous product minus number of moles of gaseous reactant. How many number of moles can be identified? Okay, every equilibrium system has a characteristic value of equilibrium constant K, which depends upon the nature of substance involved and temperature. It is a constant at constant temperature and varies with change in temperature. We know that temperature is one of the factors which affect the rate of a reaction. So, how the effect of temperature will affect the equilibrium constant? So, what they are telling, if it is temperature is constant, the reaction will also at constant. If it is the temperature is going to a variable, going to act like a variable, obviously it will change in the rate of a reaction, or equilibrium constant will also changes. Quantitatively, the effect of temperature on equilibrium is given by the integrated form of Van 't Hoff equation. Log K2 by K1 equal to delta H by 2.303 into R into T2 by minus T1 divided by T1 into T2. This is with respect to temperature using Van 't Hoff equation, where delta H is the heat of reaction, K1 and K2 are the equilibrium constants at temperature T1 and T2 respectively. Here, delta H is assumed to be constant in the temperature range between T2 and T1, that is T2 will be always greater than T1. Okay, this equation is very much important, and this will be with respect to change in temperature and which will affect the equilibrium constant. This is about rate of a reaction, the factors which affect the rate of reaction, and also how the Van 't Hoff equation will be implemented in the effect of rate of reaction, how the equilibrium constant will be written in terms of its expression, we have seen in this session. In the next session, we will discuss about homogeneous equilibria and heterogeneous equilibria. I hope you have understood completely whatever I have taught today. We will meet in the next session. Thank you.